Yeah, I've started recording. So
Yeah.
please go ahead, Susan. Thanks.
Yeah. First of all, thank you very much for inviting me. I'm really happy to be invited here at the Goa chapter for ACM because, as Professor Kamath said, my introduction to ACM was, in fact, via the Goa chapter, Maria and Professor Kamath. Thanks to them. And that time, I think it was raining extremely heavily or something like this. I vaguely remember. And almost it was going to get cancelled, my flight, but thankfully I made it, and now it has been a long collaboration with ACM, and I thank them very much for all the support they've given me. And thank you, Neha, for inviting me and getting in touch with me and keeping reminders going and so on. And also thank you everyone for those who have come here. I hope you won't regret the next 1 hour. So let's get started. This talk is about proving lower bounds or proving impossibility results. So going over to the next slide, you may have all seen the fact that square root 2 is not a rational number. So suppose I asked you, can you express square root 2 as a fraction of two integers? Then obviously you will say no, it is an irrational, you cannot do it. Many of you may have also seen the proof for how to prove this. So I would say this is an impossibility result. Let's say writing numbers as ratios of two integers is the task at hand. Then to not be able to do that for certain numbers is an impossibility result in mathematics. And just to remind you of the proof, it's a very simple proof. It can be fitted in one slide. So if we kind of quickly go forward with the slides, you will see that we can start with an assumption. So there will be a lot of overlays which probably are redundant. And then after a bunch of skipping of slides, you will see that if we start with the assumption that if square root 2 can be written as a, suppose we assume for the sake of contradiction that square root 2 can in fact be written as a fraction of two integers, then let's say it is p by q. And then as a result, by squaring both the sides, 2 is p square by q square, which is the same as saying p square is equal to 2 times q square, or that p square is even. If p square is even, then it's not very difficult to see that p also must be even. And if that is the case, again, a few slides later, we can see that p square is divisible by 4. So it's not just even, but it's also divisible by 4. And then as a result, you can see that q square must be divisible by 2. And q also divisible by 2. So what that then implies overall is p and q actually have a common factor, which is a contradiction to our initial assumption that we were able to write square root 2 as a ratio of two integers, which of course could not be further written in any more succinct form. So this proof, I think we have all seen in the past, but this is one simple example of something you've seen as an impossibility result already. And going forward, you can ask many other questions and pose them as either algorithmic questions where you actually prove computational possibilities or impossibilities. So in general, when one goes from mathematics to computer science, in computer science, we kind of care about whether a certain thing or a certain task can be done with bounds on the amount of resources we have to solve that problem. So square root 2, can it be written as a fraction of two numbers, integers or not? It's just an existential kind of question. But when we move over from mathematics to computer science, we really care about how many resources are required to solve a certain problem. So going forward, imagine the following very simple question. You're given a graph. Graph is nothing but a bunch of nodes which are connected by some edges. So some nodes may be connected, some pair of nodes may be connected, some may not be. That's a graph. You can think of it as a friendship graph on Facebook. Two people may be friends, or two people may not be friends. And if two people are friends, I will draw a line between the two. So that's an example of a graph. And one possible question one could ask is, can you properly color this graph with 3 colors? What does proper coloring mean? Use 3 colors and color the graph in a way that no 2 friends have the same color, right? So no 2 vertices or nodes which are connected by an edge have the same color. So going forward, you can see that for this particular example, actually, you can color the graph with 3 colors. You will see that take any 2 nodes which are connected to each other, they don't have the same color. So this is indeed a proper coloring for this example graph. Going forward, one could ask the following question. If I give you a graph on n vertices or n nodes, can you solve this problem of deciding whether the graph can be 3 colored or not? Can it be solved in time, say, n cube? Another way to pose this question would be, going over to the next slide, can this problem not be solved in time n cube, right? So either you try to prove to me that, in fact, this problem can be solved in time n cube by giving an algorithm for this, or you could instead show to me, just like we showed 2 numbers, square root 2 cannot be written as a fraction of 2 numbers. You could show an impossibility result for this question by showing that this particular problem cannot be solved in time n cube. Going forward, well, as it turns out, this is $1 million question, and I'm not exaggerating in any way. To be able to answer the questions written on the previous slides, either positively or negatively, that is, either to give an algorithm that runs in time, say n cube or n to the 4 or some polynomial in n, or to be able to say that it cannot be solved in, say, n cube time or n to the 4 time or whatever, you will, in either case, you will get $1 million award. This is the famous P versus NP question that you may have often heard about in conversations about computer science. So if there are any questions, please feel free to ask me at any point, or even leave them in the chat, as Professor Kamath has said. So in one way, we already have seen impossibility questions, at least. We may not have solved them, we may not have given answers to them, but we have seen such questions in computer science all the time. Okay, so going forward, let's ask a few questions about proving impossibility results or proving lower bounds. First fundamental question when somebody tells you something very exciting is why? Why should one want to prove impossibility results? All right, so let's go forward. And maybe for this slide, you can just show all the overlays, because probably it makes no sense to wait for each. So I would say that this can be motivated in 3 ways. One, by able to say that I cannot solve a certain problem in given amount of resources, you are able to show a roadblock to solving something in those resources. So this tells us that, oh, maybe this is impossible, so let's look for solutions elsewhere. Maybe there is a possible approximation to this algorithm, or there is a way to solve it in some other heuristic way, you know. So just to be able to prove fundamentally that certain things are impossible, it helps us to look elsewhere for solutions, which is sometimes very useful. Another reason why one would want to prove impossibility results is to help us understand the power of computational resources themselves. So while this question is about graphs, it's also a question about n cube time. If I'm able to say something like, oh, this is a problem that n cube time cannot solve, it also tells me something about what n cube time can or cannot do. And in some cases, maybe n cube time is not the most exciting resource bound, but maybe it could be energy. You know, if you are able to say, can I mint so many coins in this much energy? Now, this becomes a very important question about the resources itself. So proving impossibility results could be of use in that sense as well. Yet another interesting direction for proving impossibility results or motivation comes from cryptography. When somebody shows that certain functions are very hard to compute, they cannot be computed easily, they cannot be computed in polynomial time, then it immediately gives us a way of coming up with a hard cryptographic protocol. I won't be talking much about it, but if you're interested and get excited with these terminologies, feel free to Google about it. There is a lot of pop literature about this, which I think anybody in this audience should be able to understand. And finally, what excites me the most personally is it's just beautiful mathematical questions after all. So going forward, so what I tried to do was try to motivate why one would want to prove lower bounds. Maybe one or two or some of these reasons were appealing to you. I hope they were. Of course, having answered that why we would like to prove something is impossible to do, which kind of looks like a very pessimistic adventure. But like I told you on the previous slides, cryptography is possible by proving impossibility results. Just beautiful mathematics sometimes can come out of such things. So there are motivations of this sort. Having said that, okay, and also not to forget $1 million, right? So if none of this motivates you, there is this $1 million award for proving certain impossibility results at least. So now that I have tried to motivate why one should prove impossibility results, let's try to motivate or try to understand how one could prove them. All right, so going forward, the way I would like to show you how to prove impossibility results is through certain puzzles. Okay, and let me describe the very first puzzle here. Okay. So here is a naughty sibling of yours. You have a wristwatch and he has hidden the wristwatch under one of these glasses. And what he says is, I'll design a game for you. You can ask two types of questions to me. Okay, let's go forward. You can ask things like, is my wristwatch in a glass after the glass eye? Or going forward, is it in a glass before glass eye? Okay, so these are the kind of questions you get to ask him. And well, what does he say? Okay, so let's go forward. So either he can say yes or no. So he's not going to lie. Okay, so he's going to be honest, but he's going to charge you. Every time you ask him a question, you have to give him one chocolate. Okay, so that's the fee. Okay, going forward. And he could say no if the answer is no, and he could say yes if the answer is yes. Okay, so now let me ask you a question. What's the simplest strategy to figure out where the watch is? Okay, and on the next slide, we can see that one very, very simple solution is just keep asking from 1 to n. Is the wristwatch under glass 1, glass 2, glass 3, etc. up to glass n? At some point, in the beginning, he's going to say, is it after glass 1? If he says yes, you go to 2, 3, 4. I mean, if he at any point says no, that's the glass where the chocolate is. Right? So in this case, so this is a very simple algorithm, of course. Going forward, the problem with this algorithm is that, okay, if the chocolate was in the first few glasses, the wristwatch was in the first few glasses, well and good, you are doing very well. But if not, in the worst case, you could end up paying something like n chocolates, even if it was under n by 2 or 3n by 4th glass, kind of towards the end, you paid quite a few chocolates in the process. If n is really large, it's a lot of chocolates to give to your younger sibling. Okay, so can one do better? And at this point, let me pause. Let me ask whether the audience can think of something and put it in the chat or unmute themselves. I hope the question is clear to everyone. There are n glasses. You are the person, your younger sibling has put this puzzle for you, and you want to pay as few chocolates as possible, but still figure out where the fantastic, right? There are a couple of answers by Anish and Aritra and so on. Binary search, that's your answer. So let's go through the next few slides. I mean, just to motivate, if you only had like 10 chocolates, but there were 100 glasses, then, well, you will not be able to solve this puzzle using this very stupid algorithm. But as some of you have already pointed, maybe the right solution is to do binary search. So let's try that. We could go forward. So we could just go to the, through the overlays of this slide completely. Yes, perfect. Okay, and this is the typical binary search, right? You let the first pointer be pointed at 1, the last pointer be pointed at n, let the mid be pointed at around halfway between the first and the last. You ask whether the chocolate is after mid. If the answer is yes, then move the mid pointer to the, the last half of the array, or in the other case, in the first half. And as you may have already seen in binary search, you end up being only log number of chocolates. So if there were 100 glasses, then log of 100 is quite small. Log base 2 of 100 is quite small. So 10 chocolates will suffice. Just to recall for some of you who may have forgotten where this log comes from, let's look at the next slide quickly. So the recurrence that we write for such a thing is we want to search in the array of length n, but then the way to do it is we kind of reduce the search space down to n by 2 in the next round by paying 1 chocolate. So the way to write it is search n equals search of n by 2 plus 1. Once you solve this recurrence, you get log n, right? So that's how one gets log n chocolates. Great, fantastic. So, as I said, for 100 classes, 10 chocolates, you're in good shape. Okay, so let's go forward. Now, the question, of course, the low bound question or the impossibility result is, can we do better than this? So binary search, fantastic answer from some of you. And now the next question is this the best one can do? Is it the case that no matter what anybody does, wherever the chocolates are, log n, wherever the wristwatch is, log n chocolates have to be paid? Okay, so let's go over to the next slide. So imagine that there were 16 classes, okay, and the wristwatch was under the 9th class. Okay, so now what is your binary search algorithm going to do? It's going to ask, is it after class 8 or not? Right, because 16, so 8. Is it after 8 or not? It's going to say, we are going to say yes and pay 1 chocolate. Get the answer yes, pay 1 chocolate. Okay, maybe you have to go one slide further. Right, so this is 1 chocolate paid. You got the answer that it's in the second half. Next, you ask whether it's after 12th class, because that's the mid of the next. Here you get the answer no, and then you know that it's within the 8 and 12 region. Then the next query is at 10, and you pay 1 more chocolate. Again, you get the answer that it's before that. And then the next query is at 9, and then you actually figure out, okay, so you paid 4 chocolates for 16 glasses if the chocolate was placed before the in the 9th one. So what I just said was that you have to, at least in this example, right? So I gave you an example where the binary search algorithm, binary search algorithm must pay log n chocolates. Okay, but does this say that in general one has to pay log n chocolates? Not really. What we argued in the last couple of slides was that binary search, which is going to ask the mid, then the mid of the next, the mid of the next, etc., must end up paying log n chocolates. But maybe there is some weird non-binary search, super clever algorithm that could do it using fewer than log n chocolates. Who's to say that? That's not something we proved. We did not prove impossibility of all possible algorithms under the sun. All we were able to say was this particular algorithm, which is the binary search algorithm, cannot do this within log n, must use log n queries based on this example. Okay, so over to the next slide. So really, when we try to prove impossibility result, we are asking, is there any algorithm that can do better than log n? Right? So even going back to our not in the slides, just thinking back to our algorithm, our question about coloring a graph with 3 colors. It's not like you give me an algorithm and I show, oh, that algorithm cannot run in n cube time, right? That's not enough to show that something is not doable in a given number of resources. It's not enough to say that one specific algorithm cannot do it in given resources. You have to actually show that no algorithm, however clever the person may be, maybe, directly contacting in contact with the higher powers, no matter what that person has, still not able to come up with a better algorithm than paying log n chocolates, right? So this question is more general than saying a specific algorithm cannot do better than that, better than a certain resource bound. So in general, this also kind of tells you that proving low bounds is like defeating all possible clever algorithms, not just one or two or the one that you can come up with, right? It's saying something more general. Okay, so going forward, we want to say no algorithm can do better than that. And in fact, for this particular puzzle that I have laid down, in fact, if you're allowed to ask only, is the chocolate before or after a certain class, you cannot do better than log n. So one can actually prove such a lower bound. Okay, so now let's look at that. Okay, so going forward, we can view any algorithm of the sort that we saw in puzzle 1 as a tree. Okay, what is that tree looking like? Every node of the tree is a query that you can ask, like myself to the sibling, right? So in here, the tree is maybe the mid. For binary search, the tree is going to always ask mid of the current array. But in general, any algorithm that you design for solving this particular puzzle will look like the following tree, where every node in the tree is a query and it gets a yes or a no answer. And based on that, you ask the next query, so on and so forth. So for the specific example we saw, we asked whether it's before 8 or not. The answer was no. Then we asked whether it's before 12 or not. The answer was yes. Then we asked whether it's before 10 or not. The answer was yes. Then we asked whether it's before 9 or not. Then we found that the wristwatch was under the glass 9. So interestingly, if we view this protocol as a tree, then each leaf of the tree represents a specific positioning of the watch. Why? Because as soon as finally an answer is reached, when you reach a leaf of such a querying tree, you have reached a specific position in the array. And that's what, if the protocol sort of ended there, that means the watch was found there. So for some other positioning of the array, positioning of the wristwatch, say the wristwatch was under glass 12, then you would have a different leaf within the same tree, and so on, right? So now, going to the next slide, there are n possible distinct positions under which the wristwatch could possibly be. What that tells us is that no matter how you design the protocol, the tree that you come up with, for the tree corresponding to the protocol, must have n leaves, because one for each possible position of the wristwatch. But now tell me, without going to the next slide, tell me how many, if a tree has n leaves, what is its minimum depth? Any tree that has n leaves must have depth at least log n. This is just a property of any binary tree. Of course, you could have a very skew binary tree where, the leaves are just, the depth is as good as n. That's possible. But what is the smallest depth possible for any tree that has n leaves? Well, you have to at least have log n depth. Okay, so going to the next slide. What this says is that, well, if you are going to use any querying algorithm, a querying algorithm looks like a tree. because of the way the algorithm works, which is at the leaves, you actually finally know where the wristwatch is. There have to be n leaves. And if consider any tree, binary tree that has n leaves, it must have log n depth. So putting it all together, it tells you that no matter what protocol you come up with, its tree must have depth log n. But the depth of the protocol tree, in fact, stands for the number of questions you are required to ask to reach the leaf. And this now tells us that you must spend at least log n chocolates in order to solve this puzzle. Okay, so just to sit back and think about what we just did. What we did was, we started out with a puzzle. We tried to give an algorithm which we think is efficient. Then we asked, is this the best we can do? And we showed that not just this algorithm, but no matter what algorithm you come up with, nothing can be better than log n. No algorithm can do better than log n, spending log n chocolates. And this is what is a lower bound result. And what happens in any typical lower bound result is that the question, which is a computational question about resources, gets mapped to a certain data structure. In this case, it was a tree, simple binary tree, So when it gets mapped to a data structure, it's very easy to argue a little bit about the data structure. It's not typically easy to argue about all possible algorithms, but we know a little bit more about graph theory or data structures and so on. And once you transform your problem of proving lower bounds to this setting, you can actually salvage something out of it. Okay, so this was my puzzle 1 for you. It, as I said, started out with a simple puzzle. You yourselves suggested a beautiful, efficient algorithm. I tried to show to you that, what you have suggested is the best anybody can do. Okay, so you should feel good about this and ask questions if any. So I would like to put forward one more puzzle for you. Here you are the sibling and you are trying to get back to your younger sibling who has been a prankster. So you plan a birthday surprise for your brother. And you say that, look, I've kept all these boxes for you. And, the thing is that either none of the boxes have any gifts. I could be as evil as that, and none of them have any gifts. Or the other possibility is that at least half of them have gifts. I may have been very generous, and there could be more than half of them which have gifts. Now, the kind of questions the brother is allowed to ask you are very different from the ones that he allowed you to ask. All the brother is allowed to do now is he can open any arbitrary box and check whether there are any gifts inside that or not. Okay, so this is the only thing. You are not even involved in some sense. You are just monitoring the whole process. But all he's allowed to do, he opens a box, and whether there is a gift or not. But for every opening of the box, you charge him 1 chocolate. Okay, so going forward, this is what is the game. So he may open it, not find anything. He still has to give you a chocolate. He'll open it, he'll find something. Well, if he finds something, he knows already that he's in the case where there are at least half of them that have some gifts. Because if he opens a box and there is no gift inside it, then he could be in one of the 2 cases. He could be in the case where actually none of them have any gifts, but he could also be in the case where there are at least half of them that have gifts, but unfortunately he ended up picking one which did not have gifts. But in the case when he opens a box and actually finds something inside it, then in fact, in that case, indeed he's clearly in the second case. Okay, his task is to figure out which one of the 2 situations is the setting of the boxes. Okay, so to put it in pure computer science terms, basically I give you, you are my, say, younger sibling, and I give you a vector, either the entire vector 0, 0, 0, 0, 0, or the vector has at least half many ones. And you need to tell me how many of which one of the two cases is it. And the only thing you get to ask me is, tell me what is the bit xi. Okay, I hope this setting is clear. Okay, so let's go forward. Yeah, we can probably look at this slide quickly. So as I already said, right? So if first n by 2 answers are no for some reason, so what he's going to do is he's going to open in some arbitrary way all the gifts, all the boxes, and say in the worst case it so happens that he opens n by 2 of them. I have been devious and I've kept the gifts in the ones which he did not open, those n by 2 of them. So he has given me n by 2 chocolates, but now at this point he knows, one more box he'll open and then he will know that whether it's this case or the other, right? So he will give me at most n by 2 chocolates. So as a devious sibling, I can get at most n by 2 chocolates from this whole transaction, but I could get n by 2. Yeah. Okay. Going forward. So now the question is from your sibling's point of view, can he pay less than n by 2 chocolates to me and somehow get his gifts, if any? So what do you think? With a raise of hands, if you think that he can do better than n by 2. Are there any priors on each case? No priors at all. Okay, so let me actually say that if you think that you can do better than n by 2, then do thumbs up, okay? Or else, if you think you cannot do better, raise hand. So let's see what we get. Cannot do better has at least 1 vote, 2 votes. Any other opinions? There is one who says that they may be able to do better. Couple of votes for may be able to do better. Okay, great. So we have diverse opinions here. So let's go forward. Let's find out what's going to happen. So let's actually be precise, right? Let's ask the question properly. Otherwise, I'm kind of misleading you. Suppose your brother has already decided on a strategy. How he's going to ask the question? Maybe his strategy is I'll ask from 1 to n. Or his strategy is I'll do binary search, but there's no reason to do binary search. I'm not going to tell him, oh, if he opened the midway box, all the gifts may or may not be in the left half or right half or something. I'm not giving any further information, right? So I don't see why he should do any other thing, but suppose he decides some other way of opening the boxes, Maybe he knows that I love to fill my boxes from left to right or whatever. So he has a strategy to open the boxes in some way, okay? So now the thing is a question to me, can I place the gifts in a way that he must pay n by 2, right? And there were a couple of answers which, came from this point of view that, yeah, I think the brother will have to pay n by 2. Okay, so let's go forward. Yeah, so that's the evil thinking that we need to kind of invoke in us. All of us probably have it. So the question we are trying to ask is, no matter what strategy he uses to open the boxes, there exists a placement of the gifts such that he receives at least n by 2 chocolates. So if Satyanath, you were asking about priors, maybe the priors like the way he plans to open the boxes is suppose known to me. Then I think it's quite easy to see really that he'll have to pay n by 2 many chocolates. So let me just go through this thought process a little bit more. Okay, it's not like really we are going to solve this puzzle, because this puzzle, as I've written it, is not the most interesting one, but let's go forward in any case. So even this puzzle, actually, from the thought process that we built in the previous thing, we can say that actually for this also, I can think of it as a tree. At every point, I ask a question, is it in box I1? If yes, we are done. The protocol ends. If no, I ask another question, and so on. Going forward, for any ordering, so what I'll do is, I will try to skip a few slides here. So maybe you can go to, yeah, that's it. What I'm trying to say here is that let's suppose any ordering has been told to us is, so suppose as a sister, I have the tree that my younger sibling decides to query me with. Then it's very easy to argue that, well, if he's going to ask I1, I2, I3, then for the first n by 2 questions, I'll just not keep the chocolates, the gifts under those specific I1, I2, etc. up to in by 2. And I'll keep them in the rest, which is to say there exists given a prefix of his choices, I1, I2, IT. There exists a placement of gifts in the rest of the n minus t boxes, which will then force your younger sibling to pay you t many chocolates. Okay, so this is a very simple statement. I'm not saying anything non-trivial here. And some of you already guessed it. Going forward, so this kind of argument is called the adversarial argument. In current avatar, it's like a very trivial argument, shouldn't even have a name of its own, but I will just tell you something more about it. Going forward. So like I told you, the way I told you the puzzle, the question I was trying to solve was a question called promise or. Why is it a promise or question? Because it's like a or function, except it comes with a promise. The promise is either the summation of all your xi's is going to be 0, or the summation of all your xi's is going to be strictly more than n by 2. Okay, going to the next slide. Maybe one more. Okay, we'll come back to this. Maybe I needed one more slide later, I think. Sorry about that. Oh, maybe you just go back. Sorry, I'll say it in words. So let's remove the promise part from here. What is the or function? Or function is either summation of all xi's. The function becomes 1 if summation of xi's is strictly greater than 1, greater than equal to 1, and is 0 otherwise. So, in the first part, here we are saying at least n by 2 boxes have gifts, or none of them do. But the or function really is, even if one box has a gift, that's the or function. Then you should say 1, otherwise 0. You can imagine that if I ask the same question about the sibling and the game, with the thing that, okay, either exactly one of them will have a gift or none of them will have a gift. The problem will become kind of difficult for the younger sibling, right? Because if only one of them has it, he may end up having to pay n minus 1 chocolates to me, not just n by 2 chocolates to me. So in that sense, or is sort of a difficult question, promise or is sort of an easy question. And the tree I drew on the previous slide is called decision tree. And what's known is that any decision tree for the promise or function has depth n by 2. Okay, so this is a theorem. And when I say decision tree, and it's the tree I drew on the previous slide, and when I say deterministic decision tree, I mean that the questions that the younger sibling asks me are deterministic questions. Is it so and so? Is it so and so? He's not allowed to use any other resources. Okay, so let's go forward. Suppose I tell you that just to solve the promise or question that we saw on the previous slide, you are allowed to also ask randomized questions. So you are allowed to, toss coins, and depending on the outcome of the coins, you can ask questions to the sister or to you. The younger sibling can ask questions to you, which are randomized questions. Okay. Then is there a better strategy than the one that we had in the previous argument? So maybe I've said too much. Let's say the problem you're still trying to solve is there are n boxes, either half or more of them have gifts under them, or none of them do. In this setup, you want to check which one of the two it is. And now you are allowed to ask randomized questions to me. Is there any other strategy that you can invoke which is better than the one we discussed earlier? Okay, with a show of hands, if you think there is a better strategy, raise of hands. If you think there is no better strategy, even with randomization, thumbs up. Raise of hand, I see one raise of hand. And is there any thumbs up? Very good, very good. There are a lot of raise of hands. There is one thumbs up. That's great. Okay, so I'm kind of going to go with the raise of hand, guys, unfortunately this time. So there is a randomized strategy. See, if you are told that most of the times there are going to be gifts, this is one case. Most of the boxes are going to have gifts, or none of them are. So for example, let's take a more real life example. Let's say you have a room full of people where there are mostly younger people, only 3-4 older people, but mostly younger people. Then, or there is another possibility where everybody is an old person. Okay, there are these two possibilities. How will you check whether by randomly sampling, how can you tell the difference between the two settings? Well, you'll randomly pick a few people. If they happen to be old, it's more likely that it's the other setting, right? If the two situations are either a room contains only old people or the room contains mostly young people, only few old people. In these two settings, to tell the difference between the two, you just randomly pick a few people. Then if they happen to be young, very likely you are in the case where there are younger. In that case, you are certainly in the case where there are younger people. If they happen to be old, well, it's more likely that in a large group of people, if there were only few older people, the chances that you only pick old people in random is very low, right? So therefore, in such a case where either there is an overwhelming chance of one occurrence or a chance of that not happening at all being very high, to distinguish between the two, randomization actually is a good strategy. So going forward, randomization actually works for promise OR. But now if you go to OR, okay, OR is where either there is at most one in the room, or there could be so let me say it in the words that's written on the slides. You have n inputs and you have to say 1 if there is even one in your input, and you have to say 0 when all of them are 0. Okay. Now it's known that the decision tree complexity, which is what we were trying to argue, the number of chocolates you have to pay in order to figure out which one of the two cases it is, this is very high for the OR function, even if you allow randomization. So going forward, in this case, even if you use randomization, in fact, you need n by 2 many queries is proved. And this is, again, this now is not a very easy puzzle. It actually requires some thought and some work. So it is like a theorem now. Okay, so we went from promise OR to OR. We went from deterministic to randomized, and already the problem has become kind of difficult. What's known very interestingly, that if you allow quantum queries, which is something I'm not going to define in this talk, but if you use quantum queries, in fact, you can do it using only square root n queries. So I'm just throwing in these terms there. If some of you are interested, you can go back and check. Okay, so going forward, what's very interesting here, actually, so this ties up to a research level question, actually. We started with a simple puzzle about a sibling and, some sibling rivalry. But if you go from, the question I had in the puzzle, which is the promise OR question, to OR, and then you think about the quantum complexity, which I haven't really defined here, but what I'm trying to say is that though it looked like a simple puzzle, there is a deeper connection and there are interesting questions in the background, which kind of are closely related to quantum computation, for example, Shor's algorithm and Chebyshev polynomials. So just throwing in these terms here in case some of you are interested. Okay, going forward. So what we did in this talk so far is we argued what does it mean to prove impossibility result? why we need to prove them, how one should prove them. And now to wrap up, I'm going to say, what do we know about them? So, okay, I'm saying all this very interesting things. Oh, great, we have to prove such things. It will give $1 million, cryptography, etc., etc. And there are ways to do it. So let's try to figure out what's known about these. Okay, going forward. So unfortunately, what we know is merely a drop in the ocean. A lot is still unknown. Going forward. There is an interesting history to these questions, which kind of dates back to the 70s, where this NP hardness question got defined. It's at the backdrop of the Cold War, where Steve Cook and Leonard Levin proved things about what problems are NP hard. They developed the NP hardness theory. And this is a very interesting kind of literature, which I can point you to later. Okay, going forward. So this is something that's known about the results. The first problem that we talked about in the very beginning about whether a graph is 3-colorable or not. This, in fact, is a classical example of an NP hard problem. And as I said, solving this, answering either the green question, the first question, or answering the red question will actually win you $1 million. Will also, lead to a lot of interesting mathematical theories going forward. So, as I said, what's known is unfortunately a drop in the ocean. The things I have marked are sort of breakthroughs that happened over the years. And where we want to be is the part of the picture where there is a rainbow, just to indicate that, all good things are over there. We hope to have cryptography, secure cryptographic codes. We hope to have algorithms which do not need to use randomness. We can eliminate randomness from computation. So these are all desirable goals in computation. And they all happen to be beyond a landmark that seems kind of far from where we are right now. But over the years, since the time computation was first defined in the 40s, there have been, every decade or so, there have been these breakthroughs. So hopefully we will get where we want to be pretty soon. And now to the almost penultimate slide. I wanted this talk to be like an invitation to all of you to think about problems like these. Invitation to come and prove lower bounds, because we can go to the next overlay. Yeah, so what's ahead? What's ahead is we would like to have many new innovative techniques. For going forward, what we would like is finding connections between impossibility results and other areas. And I would like to assure you that there is room for everyone, in that, every new person will bring a new idea into the field, which is sorely missed and required. So I encourage all of you to think about these problems, ask questions, or write to me if you need more information. And thank you for your attention. So next slide is just my thank you slide. Thank you.